Hi, and welcome to this video on parametric equations and parametric differentiation. Sometimes it's hard to define a curve as a function, especially where the curve loops. So if we have a curve like, say, like that, where that's the x-axis and that's the y-axis, then it's quite hard to define that as y equals some function. Now we can define both x and y in terms of a third variable, a parameter, and usually this parameter we give the letter t, and each value of t defines a point xy, and we can plot this. So for example, if we have x equals t squared plus t and y equals 2t minus 1, and we have t between the limits minus 1 t 1, so we cannot go outside this range. So this is limits on t, and we can't go over minus 1 and 1. So we're asked to sketch this curve. So how do we go about that? Well, we're given some limits, so let's make a little table. And then do minus 1, choose some values, say minus a half, 0, a half, 1, and then put in values of x and y. So where t equals minus 1 in x, so minus 1 squared plus minus 1, 0. For the half, similarly, we have minus quarter, 0, we have 0, half, 3/4, 1, 2. Y, when we substitute the values of t there, for minus 1 times 2 is minus 2, minus 1, minus 3. And similarly minus 2, minus 1, 0, 1. Then we can go on to sketch this curve. So this is the x-axis, this is the y-axis. What we do here is plot these values. So say we have 2 there, 1 there, and similarly minus 1, minus 2. The curve will go from here, which is around about there, to a value about here, which is x is minus quarter, and this is minus 2, so we'll go 1, 2, so around about here, minus 2, so something like that. and stop there. Okay, when we plot the points. Now a parametric curve has a direction of motion given by increasing t. So in this case we draw this with arrows, so the motion goes this way. Also we have an initial point and we have a terminal point. Where we have limits placed upon t, we cannot go beyond this initial point this way, and we cannot go beyond this terminal point that way. Okay, so let's have a look at another example. Sketch for parametric equations x equals t squared plus t and y equals 2t minus 1. Again, let's draw a little table t, x and y. Let's choose values for t that we feel confident about. So for example, let's choose minus 2, 1, minus 1, minus a half, 0, 1. Putting these values into these parametric equations, we get for x2, 0, minus quarter, 0 and 2. And then putting these values in that parametric equation for y, minus 5, minus 3, minus 2, minus 1, and 1. Again, as we discussed previously, parametric curves have a direction of motion given by increasing t. So let's quickly sketch this curve. 1, 2. It's minus 3. So minus 1. And roughly the curve will go at x equals 2. It's going to be minus 5, which is around about here somewhere. And also at 2 it's going to be 1, which is about here somewhere. And it's going to at 1 minus, let's have a look at 0. It's going to be x equals 0. It's going to be 0. X equals 0 is there, minus 1, so it's going to go through there. And so it's going to roughly go like this, down, and across there. Again, we have the direction of motion for increasing t. At this point, t equals minus a half. At this point, t equals minus 2. Now, because we have no limits on t, we can go beyond these points this way a little bit, and this we don't have to stop there. And that's how we sketch curve for those parametric equations. Now let's have a quick look at, for example, if we had x equals square root of t and y equals t. In this case, y equals x squared, which is a parabola, downward parabola, and say we had a limit on t, so this means that it would go that way. Would have no negative side. T can't be negative, and this is our initial point, and our domain 0 to infinity. Now if we had no limit placed upon t, for example, again, if x equals t, y equals t squared, y equals x squared again, but because there's no limit on t, we get a parabola like so. T can be negative, and our domain we would get minus infinity to infinity. Okay, now let's have a look at parametric differentiation. If we consider the two equations x equals square root of t plus 1 and y equals cotangent t. Cast our minds back to the chain rule. Dy over dx equals dy over dt multiplied by dt by dx. That's the chain rule. And we use this rule in parametric differentiation with a slight difference. We just rearrange dy by dx becomes dy by dt all divided by dx by dt, and this is the rule that we use in parametric differentiation. So let's give it a go using these two parametric formulas. So for x equals t plus 1, dx by dt is square root of t plus 1 becomes t plus 1 to the half. So let's do that. So that's rearranging square root t plus 1 to something that we can differentiate, and dx by dt then becomes a half t plus 1 to the minus half, and if we rearrange that, that becomes 1 over 2 square root of t plus 1. Now let's have a look at dy by dt. Dy by dt is simply minus cosec squared t. Now we can rearrange this if we use our trig. So we have cosec is 1 over sine, the inverse sine. So minus cosecant squared t becomes 1 over minus sine squared t. So using the formula that we're going to use for the parametric differentiation, we get dy by dt, which is minus 1 over sine squared t, all divided by 1 over 2 square root of t plus 1. And then when we arrange that, we get minus 2 square root of t plus 1 all over sine squared t. And that is our answer. Okay, let's have a look at another question. So if we had the parametric equations x equals t squared plus 2t and y equals 2t cubed minus 6t. So first of all we find dx by dt, and that is 2t plus 2 dy by dt, and that is 6t squared minus 6, using our formula that we did earlier, which was dy by dx equals dy by dt all over dx by dt. So dy by dt is 6t squared minus 6, and 2t plus 2. The 6's cancel out with 2's, so we get 3, 3. So this equals 3t squared minus 3 all over t plus 1. Okay, now in this case we can factor out a 3, so this becomes 3t squared minus 1 all over t plus 1. Now this is a difference of squares, which then becomes 3t plus 1, t minus 1 all over t plus 1. These two cancel, and the eventual answer becomes 3t minus 1. And that is our answer. Quick examples of parametric differentiation and applying the rule. If we have x equals cos t and y equals sin t, dx by dt becomes minus sin t when we differentiate cos t, and dy by dt is cos t. Now, from the chain rule and the rule that we apply to parametric differentiation, we get dy by dx becomes cos t, which is dy by dt divided by dx by dt, which is minus sin t. Now we know that sine over cos is tan, and cos over sine is cotangent, so this then becomes minus cotangent t. Okay, another example, dy by dx when x equals t cubed minus t, y equals 4 minus t squared. Dx by dt, bring the 3 down, take 1 off the power, squared minus 1, and then dy by dt becomes minus 2t. So dy by dx is dy by dt, which is minus 2t, divided by 3t squared minus 1. And that is your answer. Okay, let's investigate further and look into some of the things that we can find out when we do parametric differentiation. So let's have a look. When x equals t cubed and y equals t squared minus t. So we can be asked to sketch the curve. So let's sketch curve. So what do we do here? Choose values. If we're not given some limits, then just choose some values, say between minus 2 to 2. So we'd have minus 2, minus 1, 0, 1, 2. X values and y values. When we put minus 2 into the equation for x, we get minus 8. Minus 1, we get minus 1. 0, 1, and 8. When we put the value for t into this equation, we get 6, 2, 0, 0, 2. Quickly sketch. Maximum value on this side would be 8. So 8 is there and 8 is here. Maximum value for y is 6, so we have 6 there. So roughly speaking, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So at minus 8 it's 6 up here. Minus 1 it's 2, which is about here. 0 it's going to be there. 1 it's 0, which is there. And 8 it's 2, which is about there. So this curve goes round like this and down like this, and roughly there's a turning point there. Oh, sorry, no, drew that wrong. It goes through 0, so it goes through here and then round. So pay attention to what's happening in this area here. Okay, so it's going through 0 there, going down, and the turning point is somewhere here, and then it comes back up. So let's investigate that a little bit further. With parametric differentiation, we get dx by dt is 3t squared, dy by dt 2t minus 1, dy by dx 2t minus 1 all over 3t squared, provided dx by dt is not equal to 0. Right, so when from this parametric differentiation, when t equals a half, dy by dx equals 0. So t equals a half is a stationary point. Also, when t equals a half, x equals 1/8, y equals -1/4, and these are the coordinates of the stationary points. When t equals 0, which is here, dy by dx is infinite. So the y-axis, which is this axis here, this is the x, this is the y, is a tangent to the curve at 0, 0 point. Quite often we can be asked to find the equation of the line or the equation of the tangent. So find equation of line, tangent at t equals 4. So the formula we use to find this is y minus y1 equals mx minus x1. The parametric equations we're given: x equals 3t squared minus t, and y equals square root of t. So when we put t equals 4 into this equation, that t equals 4, x equals 3 times 4 squared minus t, that equals 44, and y equals square root of t, which is 4, so y equals 2. Putting that back into this equation, we get y minus 2 equals m x minus 44. Now we need to find m, which is the slope, and to do that we differentiate. So using parametric differentiation, we get dy by dx equals dy by dt divided by dx by dt. dy by dt is a half t to the minus half, and dx by dt 6t to the power 1, so that's 6t, then minus t, which is minus 1. So we want to find this at t equals 4, and when we do that we get dy by dx at t equals 4, 1 over 2 square root of t, six t minus 1. At t equals 4, this is 1 over 4 over 23. M then becomes 1 over 92, and the equation of the line or the tangent at t equals 4 is this. Okay, let's have a look at something slightly more complicated. X equals 3t minus sine t, y equals 1 minus cos t, t equals pi over 2. Again, for the equation of the line we want to use y minus y1 equals m x minus x1. Okay, first of all let's get rid of the brackets. So x equals 3t minus 3 sine t, and y equals 3 minus 3 cos t. So putting the values of t equals pi over 2 into these equations, we get 3 pi over 2 minus 3, because sine t, sine of pi over 2 is 1, so that becomes 3 pi over 2 minus 3, which equals 3 pi over 2 minus 6 over 2, factoring out a 3, we get 3 pi minus 2 over 2, and that is our x1. For y we do the same, so y then becomes 3 minus 3 cos pi over 2. Cos pi over 2 is 0, like sine pi over 2 was 1, so this whole term becomes 0, and we're left with 3, which is y1. So the formula for the tangent or the line at that point t equals pi over 2 becomes y minus 3 equals m, which we're going to find using parametric differentiation, x minus 3 pi minus 2 over 2. So let's use parametric differentiation now on, let's use these two that we've done here. So this becomes dy over dx is dy by dt divided by dx by dt. So dy by dt, when we differentiate this, 3 minus 3 cos t becomes 0 plus 3 sine t, divided by, when we differentiate here, we get 3 minus 3. So this is dx by dt cos t. Now we can rewrite this as 3 sine t over, factoring out the 3, 1 minus cos t, cancelling the 3's, we get m equals sine t over 1 minus cos t. So that's the gradient or in this formula that we found. Now we plug in t. That's pi over 2, and we get sine pi over 2 1 minus cos pi over 2. So sine pi over 2 is 1, and 1 minus cos pi over 2, 0, and that equals 1. So that the gradient at t equals pi over 2 is 1. So let's now plug that into the equation that we have. So we have, let's do this as an aside. From here, y minus 3 equals 1. We're going to mix it, but we'll just write it down for now. X minus 3 pi minus 2 over 2 so this is m, and this is x minus x1. So we can bring the 3 over to the other side. So this becomes y equals x, we can ignore the 1, minus 3 pi minus 2 all over 2 plus 6 over 2, the 3 becoming 6 over 2. This becomes y equals x minus 3 pi minus 6 over 2 plus 6 over 2. Y equals x minus 3 pi minus 6 plus 6 over 2. 6 is cancelled, and the final formula we have y equals x minus 3 pi over 2. And that is our answer. Finally, we're going to do parametric differentiation and second derivative. So for parametric equations, x equals t squared and y equals t cubed, we know that dy by dx is dy by dt divided by dx by dt. So that's dy by dt is 3t squared, dx by dt is 2t, which equals 3 over 2t. So the second derivative written in that notation then becomes d by dt dy dx all divided by dx by dt. This becomes 3 over 2 divided by dx by dt, which we have there, which was 2t, which is 3/4 t. And that is our answer.